How to perform residential electrical inspections course. A note to students. This course is not a formal representation of current standards or code interpretation. The student may use the National Electrical Code to check any of the references and standards in this course, but it is not required. Some of the codes and standards referenced in this course may be checked for updates by the student in order to reference the most recent code adoption. Inspectors should reference their local authority having jurisdiction for the interpretation and enforcement of standards and codes in their area. This course is designed to help the student understand some, but not all, electrical installations. Local codes may have exceptions to the content presented in this course. The student should consult with their local building department in order to learn which codes are being enforced in their area. The primary responsibility for a home inspector when evaluating electrical systems in the home is the safety of themselves and their clients, both at the time of inspection and after they move into the property. This is also one of the few areas which most home inspectors would report as a defect, systems or components that were acceptable when the home was built but would now be considered defective. A lack of GFCIs in the kitchen, for example, would fall into this category. Primary safety. The home inspector should be especially cautious when evaluating the service panels. An electrical system and distribution panel can kill an inspector. According to the InterNACHI Standards of Practice for performing a general home inspection, a home inspector is not required to do anything that the inspector thinks is unsafe, including removing covers from electrical boxes or panels and exposing electrified, live, or hot electrical components within. Be sure to refer to InterNACHI's Standards of Practice for performing a general home inspection to read the requirements and exclusions for conducting the electrical portion of a residential property inspection. A home inspector is not required to remove the dead front cover of any electrical panel or box. Removing it is hazardous. InterNACHI does not require and does not recommend home inspectors to remove the dead front cover, the front cover. Inspectors should follow these basic safety rules when inspecting live electrical components. Wear protective eyewear. Wear gloves. Do not wear nylon or polyester clothing. Do not allow the client to get between the inspector and any live components. Visually inspect the panel or box without removing the dead front or cover. Do not touch a panel or box that is either very rusted or shows signs of moisture. Do not touch any panel or box that is buzzing or arcing. Frequently test for stray voltage using a non-contact AC voltage tester. Do not insert any probes or tools into electrical panels or boxes. Never carry or position a ladder near an electrical line or cable. If in any doubt about anyone's safety, defer the inspection to a licensed electrical contractor. Basic terms. Using the correct terminology. One of the challenges facing home inspectors doing the electrical portion of home inspections is getting the terminology right. Many home inspectors end up looking inexperienced or unprofessional by not knowing the correct verbiage. For example, a wire is more properly called a conductor. Here is a list of commonly used terms and their correct usage. Understanding these terms will help the inspector recognize improper panel wiring, especially in the case of grounded and undergrounded conductors. I will start with the common term, followed by the more formal terminology or description. For example, common terminology inspectors use is a hot or live wire. The more formal term is an undergrounded conductor. Common terminology includes neutral wire, where the more formal terminology for a neutral wire is a grounded conductor. A common term is panel earth ground, while the more formal terminology is the grounding electrode conductor. Common term, ground rod. More formal term, grounding electrode. Common term, main disconnect. The formal term is service disconnect. A common term, main panel. Whereas the more formal terminology is the service or distribution electrical panel board with a service disconnect. Similarly, the common term, sub-panel, has the more formal terminology, distribution panel board without a service disconnect. Common term, panel cover. The formal term is dead front. Common term, wires to outlet. Formal term, branch circuit conductors. The common term outlet has the more formal term lighting and/or receptacle outlet. Common term service to remote panel has the formal term feeder. Ampacity, the maximum current in amps that a conductor can carry without exceeding its maximum temperature rating. Appliance, utilization equipment that performs a function such as clothes washing or air conditioning. AFCI, arc fault circuit interrupter. AFCI is a device that provides protection from the effects of arc faults by recognizing arcing and de-energizing the circuit when an arc fault is detected. AWG, American Wire Gauge, is a standardized wire gauge system used since 1857, predominantly in North America, for the diameters of round, solid, non-ferrous, electrically conducting wire. The cross-sectional area of each gauge is an important factor for determining its current carrying capacity. Increasing gauge numbers denote decreasing wire diameters. AWG tables are for a single, solid, round conductor. The AWG of a stranded wire is determined by the cross-sectional area of the equivalent solid conductor. Because there are also small gaps between the strands, a stranded wire will always have a slightly larger overall diameter than a solid wire with the same AWG. Bonded, connected to establish electrical continuity and conductivity. Branch circuit. A branch circuit are the conductors between the final overcurrent device protecting the circuit and the outlets. Cabinet. A cabinet is a mounted enclosure with a swinging door. Circuit breaker. A device designed to open and close a circuit by non-automatic means and to open the circuit automatically when there's an overcurrent. Current. A measurement of the rate of flow of electricity through a conductor. Current is measured in amps. Dead front. A dead front is without live parts that are exposed to someone on the operating side of the equipment. Device. A unit of an electrical system other than a conductor that is intended to carry or control but not utilize electricity. Examples of devices are switches and thermostats. Disconnecting means a device by which the conductors of a circuit can be disconnected from their source of supply. Feeder. The feeder is a circuit of conductors between the service equipment and the final overcurrent device. Circuits feeding subpanels are called feeders. The conductors between two overcurrent devices are called feeder conductors. KC mill. In North America, conductors larger than 4/0 AWG are generally identified by the area in thousands of circular mills, KC mill, where 1 KC mill equals 0.5067 millimeters squared. The next wire size larger than 4/0 has a cross-section of 250 kc mil. GFCI, ground fault circuit interrupter. GFCI is a device that protects a person by de-energizing a circuit when a current to ground exceeds the value for the device. Line. Line refers to the incoming power. The line side of the equipment will be where the source of the power is terminated. Load. Load refers to the outgoing power. Outlet. An outlet is a point on the wiring system where current is taken to supply equipment. Examples of an outlet are receptacles, light fixtures, smoke detectors, and appliances. A switch would not be an outlet because no current is taken at a switch. Current simply passes through a switch. Overcurrent protection device. An overcurrent protection device set to open a circuit when the current exceeds a set value. Overcurrent protection devices are usually circuit breakers and fuses. Panel board. A panel board is a single panel, including buses and automatic overcurrent devices, and equipped with or without switches for the controlling of light, heat, or power circuits, and is mounted in a cabinet and is accessible only from the front. Receptacle. A receptacle is a contact device installed at the outlet for the connection of an attachment plug. Receptacle outlet. An outlet where one or more receptacles are installed. Romex. Romex is a trade name for a type of NM cable. Romex is the most commonly used wiring in homes. The proper name for this cable is non-metallic sheathed cable. A 14-2 with ground would contain 3 14-gauge conductors, one black insulated conductor, the hot, one white insulated conductor, the neutral, and one bare conductor, the ground wire. Service. The conductors and equipment for delivering energy from the service utility to the wiring system of the home. SE and SEU cables. SE cable stands for Service Entrance Cable, which is not commonly used for service cable any longer, but is used for branch circuit and feeder wiring in homes. SEU is an SE cable, and the U stands for underground. SEU cable is identified for underground use. It has a moisture resistance covering. SEU cable will usually contain 3 conductors, 2 of which will be insulated and 1 will be a bare equipment grounding conductor. SE cables are jacketed with gray, sunlight-resistant polyvinyl chloride. Nomenclature and abbreviations. Alternate ways are commonly used in the electrical industry to specify wire sizes as AWG. For AWG proper could also be written as number sign 4. The number sign is used as an abbreviation for number. NO dot 4. NO dot is used as an abbreviation for number. NO dot 4 AWG. 4 GA dot, which is an abbreviation for gauge. OOO AWG, proper for large sizes, could also be written as 3/O, common for large sizes, which is pronounced 3/0, 3/O AWG, number sign OOO, or number sign 3/O. Common wires used electric power distribution in homes can be identified by a wire size followed by the number of wires used in the cable assembly. The most common types of distribution cable, NM-B, is generally written in the following 3 ways. Number sign 14/2, also written 14-2. This is a non-metallic sheathed bundle of 2 solid 14 AWG wires. The insulation surrounding the 2 conductors is white and black. This sheath for 14 AWG cable is usually white when used for NM-B wiring intended for electrical distribution in a dry location. Newly manufactured cables without a separate ground wire, such as number sign 14-2, are obsolete. Number sign 12/2, with ground, is also written as 12-2 W/GND. This is a non-metallic sheathed bundle of 3 solid 12 AWG wires having a bare ground in the middle of 2 insulated conductors in a flat-shaped NM-B yellow-colored sheath. The color is a North American industry standard for cables made since 2003 and aids identification. Number sign 10/3 with ground, also written as 10-3 W/GND. This is a non-metallic sheathed bundle of 4 solid 10 AWG wires having a bare ground and 3 insulated conductors twisted into a round-shaped NM-B orange-colored sheath. The insulated conductors are black, white, and red. Some cable of this type may be flat to save copper. Pronunciation. AWG is colloquially referred to as gauge, and the zeros in large wire sizes are referred to as aught. Wire-sized 1 AWG is referred to as 1 gauge, or number 1 wire. Similarly, smaller diameters are pronounced X gauge or number X wire, where X is the positive integer AWG number. Consecutive AWG wire sizes larger than number 1 wire are designated by the number of zeros. NO.O, typically written 1/O, and is referred to as 1/0 wire. NO.OO, typically written 2/O, is referred to as 2/0 wire. NO.OOO, typically written 3/O, and is referred to as 3/0 wire. Know what you're talking about. Getting the terminology right will avoid a lot of "your inspector doesn't know what he's talking about" comments from local electrical contractors. Please read the article on common electrical terminology in InterNACHI's Library of Inspection articles. Simple theory. Understanding how electricity works. Electrical current is actually the movement of electrons flowing along a conductor in much the same way as water flows through a pipe. The same fundamental principles apply in the same way. The bigger the pipe, the more flow it can handle. Conversely, smaller pipes can handle small supplies. This is the principle behind resistance. An analogy to understanding electricity is a water pipe, where the voltage is the water pressure, the current is the flow rate, and the resistance is the size of the pipe. Current, which is the flow rate, or amps, is equal to the voltage, which is the water pressure, or volts, divided by the resistance, size of the pipe, or ohms. Amps equals E over R. Current equals flow rate equals amps equals I. Voltage equals pressure equals volts equals E. Resistance equals pipe size equals ohms equals R. Let's see how this relation applies to the plumbing system. Assume you have pressurized water coming out of a garden hose. When you increase pressure, more water comes out of the hose. Similarly, in an electrical system, when you increase the voltage, the pressure, volts, or E, the current, which is the flow rate, amps, or I, increases. Now, assume you increase the diameter size of the garden hose. More water will come out of the hose. Similarly, when you decrease the resistance in an electrical system, the current flow increases. Power. Electrical power is measured in watts. In an electrical system, power, or watts, W, is equal to the voltage, V, multiplied by the current, I. To understand power, think of taking that water pipe and pointing it at the top of an old water wheel. To increase the power generated by the water wheel, you can A, increase the pressure of the water coming out of the pipe, or B, increase the flow rate of the water. Measuring electrical forces. When discussing electrical supply, we use many different terms to quantify the amount of available power, the amount of work it can do, the resistance of the components, and therefore its safe operating parameters. Here are some easy-to-understand definitions and explanations of the terminology. Resistance limits the conductor's ability to allow the flow of electrons, just as friction causes losses in any pipe or ductwork. This is expressed in ohms. Electromotive force is what drives electrons along the conductor and is expressed as voltage or volts. Current is the flow of electrons driven by electromotive force through a given resistance. This is expressed in amps. Power is the amount of work that the electrical flow can do. This is expressed as watts or kilowatts. A kilowatt is 1,000 watts. Ohm's laws. George Simon Ohm was a German physicist born in Erlangen, Bavaria on March 16, 1787. Ohm started his research with the then recently invented electric cell, invented by Italian Conte Alessandro Volta. Using equipment of his own creation, Ohm determined that the current that flows through a wire is proportional to its cross-sectional area and inversely proportional to its length. Using the results of his experiments, Ohm was able to define the fundamental relationship between voltage, current, and resistance. These fundamental relationships are of such great importance that they represent the true beginning of electrical circuit analysis. Unfortunately, when Ohm published his findings in 1827, his ideas were dismissed by his colleagues. Ohm was forced to resign from his high school teaching position, and he lived in poverty and shame. However, his research efforts gained a lot of support outside of Germany. In 1849, George Simon Ohm was finally recognized for his efforts by being appointed as a professor at the University of Munich. How do the Ohm's laws help us? Ohm's laws are basically a series of mathematical models that show us how to work out safe working loads for conductors and electrical components. This allows us to understand why, for example, a 30-amp fuse should not be connected to a 14 AWG wire. That's about resistance and overheating wires. Ohm's laws define the relationship between voltage, current, and resistance, where I is the current, measured in amperes, amps/A. R is the resistance, measured in ohms. E is the electrical potential, voltage, and W is power, measured in watts. Common Ohm's laws are watts equals volts times amps, or W equals E times I. Another would be amps equals watts divided by volts, or I equals W divided by E. Amps measure current. The volume of the current, the number of electrons flowing past a given point per second, is measured in amperes or amps. Volts measure pressure. The pressure under which electricity moves is measured in volts. Electricity arrives at household circuits at a pressure of 120 or 240 volts. Watts measure power. Power is measured in watts, and you can compute wattage by multiplying amperage and volts. Examples. Assume that a standard incandescent light bulb is drawing half an amp from a 120-volt circuit, uses 60 watts of power. 120 volts times 0.5 amps equals 60 watts. To calculate amps, divide watts by volts. Assume an electric clothes dryer is using 240 volts and is rated at 7,200 watts, pulls 30 amps. 7,200 divided by 240 equals 30. This means that the dryer must be protected by a 30-amp circuit breaker, and the wire carrying current to it must be number 10 copper, which is rated for 30 amps. How much does it cost to operate my portable electric heater? An electric heater wattage is usually given on the unit itself. Assume it is 1,000 watts. Assume that the heater is used an average of 45 hours during winter months, half hour per day for the 3 winter months, and the utility's electric rate during the winter is 0.068 cents. Then, 1,000 watts divided by 1,000 equals 1 kilowatt times 45 hours of operation, equals 45 kWh times 0.068 cents equals $3.06. Now let's assume that we have an 8-amp heater. The calculation changes just a bit to 8 amps times 120 volts of household current equals 960 watts divided by 1,000 equals 0.96 kilowatts times 45 hours equals 43.2 kilowatts times 0.068 cents equals $2.94. Conductor sizes. Understanding the limitations of conductors. As we saw with Ohm's law, resistance is key to a conductor's ability to safely deliver the amount of power that a circuit needs. Think back to the pipe. The bigger the pipe, the lower the resistance. Conductor material. When evaluating electrical supply, we need to recognize that copper and aluminum conductors are not the same. Although they are both commonly used in residential supply, copper inherently has less resistance to the flow of electrons than aluminum does. For this reason, aluminum conductors are always 1 to 2 sizes larger than the equivalent copper one for any given amperage. Jumping a bit ahead, single-strand or solid aluminum branch circuit wiring should always be fully evaluated by a licensed electrical contractor. Multi-strand aluminum wires, as seen on service entrances and high-amperage circuits, are not a problem. This issue is studied at greater length later in the course. Conductor size. As we have seen, for larger amperages, we need larger conductors. Please refer to the table in the course for a general guide to sizing conductors for feeders and services. Overcurrent protection required. All underground branch circuit and feeder conductors must be protected by an overcurrent device. Overcurrent devices consist of circuit breakers or fuses. They are installed at the beginning point of the circuit where the conducts receive their electrical supply. The breakers prevent conductors from carrying current above the determined allowable ampacity. The breaker will automatically open the circuit and protect the conductors if the current is too high and may create a very high temperature hazard. For small conductors commonly seen by home inspectors in residential buildings, the rating of the breaker must not exceed the ratings for the conductors. AWG stands for American Wire Gauge, which is a standardized wire gauge system. Key point: the maximum breaker rating must not exceed the allowable ampacity of the conductor. The smaller conductor sizes are normally single-strand conductors, but as they get bigger, they switch to multi-strand so they can be easily worked. It is unusual to see a conductor of less than 8 AWG to have multiple strands. Again, we will come back to it later, but remember to look for single-strand or solid aluminum branch circuit wiring, especially in homes built between the mid-1960s and the mid-1970s. The presence of solid aluminum branch circuit wiring in a home is a major defect. If you observe indications of such wiring, type and deem it a defect, report it.